Konnichiwa. Thank you for coming today. Today's talk is called Building Scalable Complex Applications on Google App Engine. And this is actually a talk originally presented by Brett Slatkin at Google I/O, and he was gracious enough to lend me the slides for today so I can present for you. So let's talk about what we're going to cover today. We're going to talk about two main things. The first is list properties. We want to talk about what they are and how they work. We're going to use a specific example of microblogging, which is like Twitter or Jaiku. We're going to talk about how list properties can maximize the performance of your application. And the second thing we're going to talk about is merge join. What it is, how it works, and we'll show you some magic that you can do with list properties. We're going to do this in the context of modeling the social graph, so the friends that I have and where they live. So list properties, what are they? In the data store, you can store regular properties like maybe a number, a text field, a date, but you can also store multiple values for each property. And it's simply as easy as this. You define a model class, let's say favorites, where we're going to store favorite colors. We have a username property, which is a regular string property which contains the username, and a colors property, which is a list property. This is where we're going to store multiple values. And we simply can do that here. Favorite.colors equals red, green, and blue. A list property is an ordered list. That means that red, green, blue is a different list than blue, green, red. It's also a list that maintains its order. So when I store this in the data store and retrieve it, the order is maintained. And I can query any of these values with an equals filter. That's very powerful. That's something we'll look at later in the presentation. I should point out that the sort order is not useful unless you have a composite index. But usually this is something you can work around. So how can we use list properties? We can use it to track lists of related things, like my favorite colors, red, green, and blue. We can use it to store multiple parallel lists, giving us tuple-like data. For example, we can store the names of 3 players and their high scores. And we know that the first value, 1,290, is associated with Joe. The second value, 54,800, is associated with Jane, and so on. We can do this with 2, 3, 4, any number of list properties that we like. List properties are fairly easy, so let's compare them to a one-to-many query. If we did not use list properties, and we just used regular properties, we might do something like this. We would define users in one entity, and we would define colors in another entity, and we create a third entity, which you see here, describing favorite colors, which joins users with their colors. And we could select from that table with a select from favorite colors, where username is some value. And it would return us the list of usernames, but then we would have to fetch those users. So there's a little bit of extra work involved. List properties work a little bit better, and they're great for answering set membership questions, like, is the color red one of my favorite colors, or is the color yellow one of my favorite colors? And if we do that with our original example, using list properties, we can do everything in a single query. We can say select star from favorites where colors equals yellow. And the colors list may, in fact, contain many colors, and only one of them is yellow, but we still get the answer. And the select star gives us all the values. So our query is actually more efficient here than the one-to-many query we saw on the previous slide. What we do is then take the results, and we can grab the username for each and store this in a collection. That's this last line of code. List properties are great for fan-out capability, where you have a kind of a one-to-many relationship. And it allows you to very efficiently cut across all your data and find any user, maybe that has favorite color yellow, across all favorite entities in the database. Another reason to use list properties is that it avoids storage overhead. It can save you space in the data store. Each item of a list property only has an index entry. There's not a separate entity entry as you would normally have. And there's also no entry in the by kind index. You may know if you've used kind index is a special index that's automatically created for you for each entity. Since we're using properties and not entities, we don't actually have an entry in the by kind index, so that saves us some room. There's no key for entities in a one-to-many relationship. So our colors, red, green, and blue, are simply properties on the user and not separate things. Ultimately, this can really save you a lot of storage space. And it's actually simpler to understand than a normalized schema that you might find in a RDBMS scenario. So if you do this in an RDBMS, you would probably set up a users table, a colors table, and then you have a third table, which is the intersect table, which contains users and each of their colors. And you'd have one row for each favorite color for each user. With list properties, you can actually put everything in a single entity, and it's a lot simpler to understand. There are a few gotchas with list properties, a few things to watch out for. The way the data store works, you actually will pay a little bit of a serialization and deserialization cost when you access the entity. The data store is a little different from an RDBMS in that entities and their properties are stored very compactly. And because of this, they need to be deserialized when you read them, and they need to be serialized when you write them out to disk. List properties only work with a sort order if you're querying a single list property. If you try to do it with multiple list properties, you get what is called an exploding index. That's when you have, say, 3 values times 3 values equals 9 index values, or 10 times 10 times 10, and you very quickly get a very large number of index entities. That's what we call exploding index entities. So we have to watch out for that. But usually, you can find a good solution that will work. So let's look at a concrete example, microblogging, something like Twitter or Jaiku, which is essentially a publish-subscribe or a broadcast-multicast model. Users send a single message, a status message, a piece of information, short bit of text, that goes out to many other users. And it's a great example of what we call fan-out, from one to many. One user action causes a lot of work in the system. Work leaves a large amount of data that needs to come to the surface or accessed. And frankly, fan-out is hard. It's difficult to do this one-to-many model. Fan-out can be inefficient and can require duplicate form data, which you don't want. If you send a copy to n different users, you might do something like this. I send my message, and then I create a copy of that message for each user that it needs to be delivered to. If I have 3 users, as this example, that's okay, maybe. But if I have thousands or millions of users, that's a lot of data to be copied. That's fan-out done wrong. Efficient fan-out would avoid copying data. And we can, in fact, do this. Instead of sending the message and copying it, we can just send a reference. We can have each of those users get a unique identifier that will point to the original message. This saves us in storage space, computing time, etc. So let's compare with the RDBMS scenario. We would start with a users table, and we define all our users. We'd then add a messages table, and we'd list each of the messages. And then we need our intersect table, the users messages table. And this maps each message to the user that wrote that message, or each user that that message needs to be delivered to. And then at runtime, we would do a join. We would query against all three tables and combine the results to figure out which messages need to be sent to which user. So if we were to do this, the query might look something like this. We would select from the messages table. We need to join on our intersect table using the message ID. And then we would search for users with a particular ID. Now, on App Engine, you may have heard that we have no joins. So how do we do this? Well, list properties. That's what we're talking about, and they can help us. So let's try it. What does it look like? We create a message class, and we put in the sender. This is the person who typed the message. And we enter the body. That is the actual text of the message. And then we add a list property called receivers. This is a list of all people, all users who should receive the message. And that's it. It's one entity, not three different entities in the data store. So it's very simple. To select which messages should be received by a certain user, we can select star from message where receivers equals me. And I can find all the messages that belong to me. And that's it. It's real easy, and that's in fact how Jaiku works today. I would also like to show you the example with Java using JDO. JDO is a persistent standard. JPA is another one. In this case, I will show you JDO. We create a public class called message. We create a primary key, and we use an identity strategy. This is a long, it's just a number. We take a text property for the sender, a text property for the body. This is the same as the previous slide, but now in Java instead of Python. And we create a list of receivers. This is our string list property from before. And that's it. That's our simple class, and we use the same query to access it. Now, to do that query in Java, we write things a little bit differently. We have to get a persistence manager. We have to create a query on the message class. Then we set a filter. We say where users equals, say, me. And then we get a list of results when we execute that query. It's very simple. So let's talk a little bit about list property performance. Index writes on App Engine are done in parallel on Bigtable. That's because Bigtable is distributed. There are many, many machines that serve your App Engine application. And your index is distributed across those machines. So when you write, say, 10 updates because your message needs to be delivered to 10 people, those 10 writes may in fact go to 10 different machines, or maybe they go to 7 different machines. But the point is that this happens in parallel. It's very fast. We can update 1,000 items with 1,000 rows at the same time. So it can be very efficient. It scales linearly with the number of items. So twice as many items can take a little bit longer than, say, half of that. There is a practical limit of 5,000 index properties per entity. And later on, I have some workarounds for that, too. The storage cost using the data store is about the same as it would be in the RDBMS scenario with 3 tables. For the RDBMS, your third intersect table would contain 2 columns, 2 values. That would be the user key and the message key. That's how it joins the other 2 tables together. For list properties, we would have the list property value, which is the user to be delivered to, and the entity key, which points to the actual message. And those take up the same amount of space in the database. List property performance. There is this downside of the serialization, deserialization overhead. Again, I'm looking ahead a little bit because we actually have a solution for that. To explain the serialization, deserialization, I think I should mention that the data store stores all the name value pairs in what is called a protocol buffer. This is a very compact way of storing data. For writes, it's okay that it's a little bit slower because writes don't happen that often. When I type my message and need to deliver it to 100 friends, that just happens one time. But reads are a little bit different because the deserialization has to happen every time each one of those 100 users logs in to retrieve their messages. So reads are a little bit too expensive for this, and they're slow in wall clock time. That is the amount of time that elapses while this happens. It costs too much CPU time to do this deserialization. That's unnecessary. And here's a link to the protocol buffers that we have open source, so you can read more about protocol buffers. Querying messages should only return the information I'm interested in and not all this extra data that needs to be deserialized. We don't care about the list properties after we search for the messages. We just want the message and the text and the sender. So when I log in to get my messages, I, in fact, want to see who sent the message and what the message is, and that's it. So what if we could do that? We could avoid the serialization cost, and that would be great. Ideally, we could do something like this in GQL. We would only select certain values, select this, foo, bar, from my model, and avoid all the other ones. But because of the protocol buffers, I can't get to individual values. The data store has to deserialize the entire protocol buffer in order to get to individual values. So the only thing that we actually allow is select star from my model. So the problem here is that everything is stored in my model, in the message class. And really, maybe we can split that up. And in fact, let's do that. And we'll call that relation index entities. This is not an official name, but it's something that we kind of came up with to talk about this. And we have a few slides to introduce you to relation index entities. The concept is that we take the message class and we split it into two parts. We split the message, we let it contain only the information we need, so that when we do select star, we get exactly all the properties we want and nothing more. Then we split off a separate part called the message index. This is the relation index entity, and it has only the relationships that we're interested in. This is the entity that creates the indexes that we'll use to find our messages. So what does that look like? Well, the message, just like before, has a sender, the person who typed the message. It has a body, which is the text of the message. But instead of the receivers being here, we have a separate entity called message index. And there we put the receivers. Now, we have to associate these two together. And we'll do that. We'll put them in the same entity group so we can do transactions across them. But we also get another benefit, which is that the message index is a child of the message parent. And so that when we find the key for the message index, we in fact have the key of the message parent, because we just chop off the last part. So the message is that first part that you saw. The message index is that second part that you saw. Now, to retrieve our data, we do something called a key-only query. It's a special syntax where we use underscore underscore key underscore underscore. And the App Engine data store does something special. When it sees this query, it does not deserialize the properties. It instead just returns the key for you to access. So we can do this query to find my messages, select key from message index, where receivers is me. And then we take the return keys and we transform them into parent entity keys. And we simply iterate over the results, and we call key.parent. This takes the child key and chops off the last piece and leaves us with the key for the parent. Once we have that, we can fetch all the message entities, all the messages that should be delivered to us in one batch. We say messages is db.get. We feed it a whole list of keys. So this can be very efficient because those retrievals can happen in parallel. That's because App Engine has a distributed data store. And this is in fact how our data store works under the covers. So relation index entities, we can conclude that performance is much better than what we had before. Writes cost about the same because we're storing about the same amount of data. and the same number of indexes, but reads can be up to 10 times faster, simply by splitting our message into a message and a message index. We get the best of both worlds with list properties. We get low storage cost, which is great. In fact, the same storage cost we would have in RDBMS. And we get low CPU cost because we don't pay the extra deserialization overhead with protocol buffers. But we can do it even better. We can make our indexes a little more scalable. What if we need more than 1,000 entities or 1,000 properties in our receivers list? Well, then we simply can write multiple message indexes for each message. We can, if we want to go even further to millions and millions of followers, we could maybe use task queues, which haven't quite been released yet, but are something that's coming really soon. And in fact, there's a talk at I/O that you can watch that goes into it in great detail. And that would give you, if you combine relation index entities with the task queue, it would solve the million fan-out problem. The problem of I write one message and it needs to be distributed to a million users. And when I do multiple message indexes, I don't need a schema migration. Everything, my code still works. So this is what it looks like. We have multiple message indexes for a single message. And each one of these message indexes can have up to 1,000 values for the receivers column. And I can create many of these entries at once. Now, the second part of the presentation, we want to talk about merge join, which is a type of query, and we'll still use list properties in merge joins. So what is the merge join? Well, people say that we don't support queries on App Engine. But the fact is that it is true that we don't support natural joins, or inner joins, or outer joins, but we do support merge join queries. This is a special type of query that has some interesting properties. It's a type of self-join query, a query that connects an entity back to itself. We can combine many equality tests in that query in a single query. So we can make multiple test conditions in a single select statement. And we can determine Venn diagram type overlaps, like this example, where we organize all the animals that we have in our database. And some animals have horns, some have 2 legs or 4 legs or 8 legs, but not all of them match the same criteria. And we're looking for animals that have spots, horns, and 4 legs. And we're hoping to find cows in that list. So let's see if we can do that. But first, why would you use merge joins? Well, it's great for exploring your data. It allows you to find things, filter in your database. You can do a large number of filters in a single select statement very efficiently. There's no need to build special indexes in advance, so you can write ad hoc queries. It can be done very efficiently and reduces the cost. And it provides some additional functionality, like, for example, in Gmail, if you wanted to filter on multiple labels, on whether a message is read or unread, the number of replies, you could combine that into a single query. So let's look at an example of our animals in using merge join. We're going to create a has property, which is a string list property, a color, which is a simple plain property, legs, which is an integer value. And we're going to query everything from animal where color equals spots, it has horns, and legs equals 4. That's our query. Now, it's not really available in raw Bigtable, but it is available in the data store, which we've built on top of Bigtable. There are similar optimizations in other database systems. All property indexes are sorted in lexical order or in alphabetical order. And I'll go into this in the next slide, why that's very important. The data store does what's called a merge sort at runtime. It merges multiple results that are already sorted together, and we will walk through that. It's also called a zigzag algorithm, and you'll see why in a moment. but we zig and zag through the result sets from left to right around. And it's very efficient because we can scan Bigtable, which is distributed, in parallel. We can retrieve legs equals 4 result sets and has equals horns and has spots. And all 3 results can be merged together very quickly. So let's look at it. Remember, what you're going to see are index values, and they're represented here in tables. So, for example, we have some values here. We have animals that have color equals red, color equals spots, and color equals white. And you'll notice here that everything is sorted alphabetically or lexically. In fact, the red comes before the S in spots, so R before S. You also notice that here, color equals spots, comma, key equals, those are the same in these 2 rows. But what's different is that bear comes before cow. Again, this is all sorted. Now, if we expand this and add to it some other properties, this is all in the same big table. Has equals hair is here, and legs equals 2, legs equals 4. Again, we have this property. C becomes for H becomes for L. The entire index is sorted. Now, even though it's sorted in one big table, there are so many entries from your application in there. The big table can distribute this. And in fact, even if you have a few entries, it will distribute this across many different machines. So let's look at that. Let's split it apart and pretend that they're in 3 different locations. These are the result sets that we're looking through. So how do we find our cows? Well, we start searching on one of the result sets, and we go to the very first row that meets the condition, color equals spots. As soon as we have found that row, we jump to the next result set, and we look for has equals horns. We grab our first entry. Now we have these 2 rows, and we see that in number 1, the result is key equals bear. That's our first answer. And in number 2, our first answer is key equals cow. Now bear comes before cow. So what we know is that bear is not a right answer. We need to advance number 1 to the next row because it's not a match. So we try a higher value. We try the next one. The next one is cow. This is great. Now we have the same key value on both result set. This is called the zig. We go to our third result set, and we look for legs equals 4. We find key equals cat. Well, cat comes before cow, so this is not the right result. So we need to advance number 3 down 1. And lo and behold, we find key equals cow. This is the zag. Well, all 3 values equal the same key. All our conditions are met. We have our first answer, key equals cow. We've found our animal, our magic animal. Let's take a look at another example, the social graph. This is users that have profiles and a set of friends. We'll look at merge join on list properties and show a little bit of magic there as well. It'll allow us to answer queries on relationships. We can ask questions about who are my friends? We can also ask who are my friends in location L? Like who are my friends in Tokyo? Who are my friends in San Francisco? Which friends do I have in common with person P? So which friends do I have and my friend Joe have that are the same? We can find the overlap. Which friends do I have in common with Joe in Tokyo that we could meet up with? To be a little bit simple, we will assume here that all the relationships are two-way. So if I'm Joe's friend, then Joe is my friend. But this also works in what we call a directed acyclic graph. A directed graph is one where there's a direction in the relationship. So I am Joe's friend, that's one direction. If he is my friend, that's the other direction. Acyclic means it's not a circle. So I have friends with Joe, he has friends, but at the end it doesn't come back to me. It's just spread out. So this is what a set of friends might look like. we have Bob and Mel who live in New York, who are friends. Bob is friends with Stu, who lives in San Francisco. Who's friends with Willie, who's also in San Francisco? Willie is friends with Lenny, who's friends with Carl, and those two live in Chicago. Now, if we look for mutual friends of Willie and Carl, say, who are friends with both Willie and Carl? We find it's Lenny. Now, if we want to look for mutual friends of Bob and Willie, but only in San Francisco, we can also find the answer. It's Stu. If we did this with an RDBMS, you would probably again do 3 tables. You would create a person table, and you'd have each user and their location listed. You'd have a friends table, sorry, not 3 tables, 2. We have users table, and then we have this join table that joins users to themselves. So we have 2 columns in the friends table. We have user A and user B, and this indicates a friendship. A is friends with B, and B is friends with A. If we want to issue a SQL query to find the friends of, say, user X, we can do something like this. Select star from friends. We can inner join on the friends table using the user ID. And then we specify that one of those users is X. We can also filter by location, and that's very easy. We just add and location equals San Francisco. Now, it gets a little bit trickier if we want to do something like friends in common with both X and Y. Our query starts to get a little bit more complicated. We still select from the users table, but now we have to join on the friends table 2 times. We have friends F1 and friends F2. And then we have to be careful how we write the query. We join the users table with F1. We join the users table with F2. The F1 table, we have to match up with X. The F2 table with Y. And then we have to join F1 and F2 together as well. So it's easy to make mistakes here. Now in App Engine, there were no inner joins like this one. So what do we do? Well, maybe list properties can help again. Let's create a class person, a location field, which is just a simple string property, and then a friends field, which is actually a list property. And that's it. That's our model. We don't have 2 tables. We just have a single entity with 2 properties, a regular property and a list property. Now, if we want to find those friends in common, we can select star from person, where friends equals 1 and friends equals 2, the other person. And location is San Francisco. And we pass in the values of myself and the other person. And that's it. That's much easier than the inner join you saw. Much harder to get wrong. But it's pretty interesting. If you're used to SQL, this may seem strange to you. We have friends equals 1 and friends equals 2, and 1 and 2 are different values. If you do this in a SQL database, you'll probably never get an answer. Your result set will always be empty. But this is the magic property on App Engine Data Store, where because friends is a list property, and as long as friends has multiple values, it is in fact the case that this can be true. Friends, another way to look at this, instead of the equal sign, imagine that it says contains. So select star from person, where friends contains number 1, and friends contains number 2, and location is San Francisco. That makes a lot more sense. And that's it. We can add as many equality filters as we like. So we can have friends in common with myself and Joe and Jane. Quite easy. Now, the merge join scales with the number of users and size of the result set. It's best for queries with few results. So less than 100. So most queries are a good example of this. similar access performance as list properties, and we get the same kind of read-write speed. There's no extra storage overhead for doing merge joins. We just have this runtime merging of result sets that happens. And we can avoid the serialization that we had with relation index entities. There are, of course, a couple of gotchas or things to watch out for with merge joins. We'd like you to watch out for pathological data sets. That means poor data sets that don't work very well. These are ones with too many overlapping values. You saw the zigzag. If we have to zigzag, zigzag, and we keep going back and forth between many result sets, that may take a lot of effort, a lot of CPU time, and won't work very well. So you have to watch out for that. Also, this doesn't work with composite indexes because of the exploding index combinations that I talked about before. What it does mean is that you can kind of work around this. You can sort in memory instead. So when you do this join, you look for, and you apply many different filters, and you're unable to add an order by clause in the SQL statement. What you can do is retrieve the results, and then in memory, when you have your list of friends, you can sort them. So let's wrap up and look at what we covered. We used list properties and merge join for many things. We solved the fan-out problem, the one-to-many problem. We could store geospatial information. That's information on maps, locations. We can store relational graphs, who my friends are. And we can store fuzzy values. So I kind of advise you to think about how to convert your queries into set membership questions. Can you write your query in such a way that you ask the question, does it contain a value? Is yellow one of my favorite colors? Is Stu one of my friends? These are set membership questions. I have a set of friends or a set of colors, and I want to test if the value that I'm looking for is in that set. We can compute membership at write time. So we create our lists at write time. We write out the values red, green, and blue. And then at runtime, we enjoy very fast reads. We just search for red, and we get our value back. It's very easy. I want to leave you with a few URLs of where you can read more information. This first one, code.google.com/appengine, contains the documentation, links to the community forum, articles, and more. There are also a couple of demos that Brett created when he produced these slides, and they're available on appswat.com, including source code. And what he's done is he's modeled the publish-subscribe, so the microblogging scenario that you saw earlier. And he's also modeled the directed acyclic graphs, so the friendship graphs. And so you can play with those. You can enter values, submit them. You can look at the source code. They're really good to look at. And then my contact information if you'd like to send me an email or ask a question afterwards. Thank you very much. I think we have time for a few questions. If someone would like to ask a question, please raise your hand, and we can have a translation if you like.
Sorry, I couldn't figure out why you can speed up your query by splitting your table into two with the relational index field.
Oh.
Could you explain more?
Yes. Let me just go to the slide. Sorry, it's a bit slow. Almost there. So here we had a single message, and we store the sender, the body, and the receivers in a single entity. And because of everything being stored in a protocol buffer, it's very compact in the data store. But when we retrieve it from the database, App Engine has to deserialize the information. It has to take it apart. And if my receivers is a long list of 1,000 entities, 1,000 users, then it has to process 1,000 entries and put them in memory and give them back to me. And that takes extra time. When we create the relation index entity, we split off the receivers. And we actually never deserialize it. We only use the index for the message. So in the message index case, let me go to that. It's a little bit different. Here, when we write the message index and we write 1,000 values, those 1,000 values are serialized into a protocol buffer and saved on disk. But we will never read those again. We don't care about those anymore. At the same time, the data store will write out 1,000 index entries. Each index entry says receiver equals A, comma, key equals user X. Receiver equals B, key is 1, 2, 3. There'll be 1,000 entries like that. And when I search, when user X logs in, they do a search on that index, and they find only their entries. So maybe they have 3 messages waiting for them to look at. And we do a key-only query. So App Engine gives you back the key, but we don't get the protocol buffer with 1,000 entries. We never look at that, a key-only query. We take those 3 keys for those 3 messages, and we chop off the last part and throw it away, which gives us the key of the parent. And then we do a batch get and say, App Engine, please give me 3 messages. And App Engine will return the sender and the body for 3 messages. So we deserialize the protocol buffer for the message class. But that's very fast because it's only a sender and a body. So the trick is here that the receivers, which may be 1,000 values, is stored in a protocol buffer one time and then never accessed again. We leave it there. We only use the index, and the index is split into 1,000 different values, and each user that logs in only gets their one value. That's the trick. Does that answer your question? More questions?
もしセンターが検索条件に入っていたとしたら、どういうクラス分けになるんですか？同じでいきますか？
Can someone translate? I'm sorry.
So if the sender also a search condition, then the same.
The sender is also a search condition. What we could do is we could, in the message index class, so I think your question is, what if the sender is also part of the search condition? Well, what we can do is we can combine receiver and sender together as one value and store that in the message index class, so it's a single key. Another way to do this would be to create 2 list properties on the message index class, one for receivers, one for senders, and do that tuple-like data where you have 1,000 values, 1,000 values, and then kind of use the merge join trick to get to it. I think the better approach is probably create a single combination of receiver plus sender, combine that into one value, and store combined value on the message index class. And then when you do your query, you say where sender plus receiver equals, and then your string is sender plus receiver. So you're looking for one value, but it's 2 values connected together. Does that answer your question? Any other questions? Hi. Last question. This is the last question.
範囲指定で検索する場合とか、not equal で検索するっていうことは可能ですか？
I hope could someone translate? Sorry. ありがとうございます。
範囲指定で検索 How to query between A and B or not equal query can 可能ですか？
Okay, so I think the question is how to query both A and B with a not equals query. It's important to note that a not equals query on App Engine actually results in two queries being issued to the data store. App Engine's first searches for values less than the value, and then for values greater than. So if I do a search where colors not equals red, then the App Engine does two queries. It says, find all colors less than red. So in the alphabet, they come before red. And then another query, all colors after red. And those two results get merged together. I hope that answers your question. So yes, you can do not equals query. But currently it's not implemented in, I think, the JDO implementation on Java. But if you use the data store API, you can get to it. So that is the last question. I do want to say one thing. Today we have office hours. I think it's the 3rd floor. There's tables set up, including App Engine. Please come by. John and Lindsay and myself will be there throughout the day. We can answer very specific questions, talk about your problems, hear your experience. We'd really like to hear what you think of App Engine, what we can do better, what we're already doing better. Thank you very much for coming.